Mathilicious is, how we're doing PBL, and then we'll get to questions at the end. And thank you guys all for joining us. So hopefully you can all see the screen. So just a little bit of background about myself. My name is Karim, and I am a former middle school math teacher. I started my teaching career in Arlington, Massachusetts. I then taught in Greene County, Virginia, 8th grade math before teaching middle school math in Harlem. And then I was a middle school math coach in Alexandria, Virginia. So if you're a teacher, I'm right there with you. And as a middle school math coach, I started working with teachers to develop lessons around real world topics, and that eventually became what is now Mathalicious. So what we're doing at Mathalicious is we write lessons around real world topics. So we provide classroom teachers with lessons that help them teach the Common Core standards through real world topics that engage their students to think about the world a bit differently. Before we get into this, let's just take a step back and look at what we as math educators are facing. According to a 2009 Raytheon survey, 61% of middle school students say they'd rather take out the garbage than do their math homework. And when you ask them why, oftentimes they say, I don't know what this means. It seems like a bunch of random steps to me. I don't know what this means, and I don't know when I'll ever use it. And so much of this comes down to, of course, the way that we teach math traditionally. We oftentimes teach it as a procedural step-by-step, do this, then do this, then do this, then do this. There's an absence of critical thought, and instead it feels like a recipe sometimes. So let me X out of this and just come back to the chat to make sure we're all good. Everybody good? Everyone is able to see the presentation? Perfect. Thank you, guys. All right. So this is what students think of when they think of math oftentimes. And to put this, to really make this concrete, let's just look at how a traditional skill, a very important skill in Algebra 1, tends to be taught. So calculating the equation of a line between 2 points. What is the first thing that if you were going to walk into a traditional classroom, maybe not your classroom, but a traditional classroom in the United States, and this was about to be taught, what is the first thing you might expect the teacher or the textbook to ask students to do? If you could just take a moment and type that into the chat window, we'll see if everyone kind of has the same prediction. So again, first thing you expect a teacher to say in teaching this concept. Okay, we've got some, they would find the slope, calculate the slope. All right, so let's go through this. So first thing is I would say is write the general form of the equation. I imagine we oftentimes just skip over that when thinking about this. But then we would say, yeah, we tell students to find the slope, and we often define slope as rise over run. And so hopefully a student calculates the rise correctly, and hopefully he or she calculates the run correctly and gets a slope of 1.5. Of course, we know, if you've ever taught this, we know that students are not going to get this right. Many students will calculate the rise as 2, and many will calculate the run as 3, and then you've got to address that misconception, although it can be argued that it's not a misconception because there was no conception in the first place. It just seems, again, like a bunch of random steps. But assuming students get it right, then what do we tell them to do once they found the slope? Well, I can't see what y'all are chatting, but hopefully, I imagine some people said we tell them to plug the slope into the equation. And so now we've got this, and then what do we tell them to do? Well, we say pick a point, and students say which point, and we say it doesn't matter, and students say why not, and we say cuz, and they're like whatever, plug in a point. Hopefully they pick the right coordinates. You know, you can imagine that some students are going to put 4 in for y and 17 in for x, or there are any number of things that could go wrong, but let's just say that they do this correctly, then we tell them to subtract 6 from both sides, and voila, we've got the equation of a line. Now let me X out of this, and my question is, and what I'd like for us to chat about for a moment is, if you're an 8th grade student, Algebra 1 right now, but 8th grade in Common Core, if you're an 8th grader and you've never seen linear functions before, how do you think you're going to respond to this series of steps that you were just faced with? Is this going to make sense? So let's chat about that for a moment. All right, so memorize or die trying. Nadira's like, what is going on, right? They wouldn't remember the formula. I wouldn't wonder how I could use this in real life. Everyone, yeah, exactly, right? I mean, we've all probably been there. I certainly learned linear functions like this, and to be honest, I probably taught it like this too. Okay, so we can understand then why students react the way that they do. And yet, I think we can all agree that this is how linear functions is traditionally introduced. So let's take a moment and let's just have a little chat about why do we think teachers oftentimes do this? I mean, we do it for a reason, so what might that reason be? Okay. It's how we were taught. It's what they know. It's how we learned it. So it sounds like Laura, Talania, Sherry, or rather Inns, I guess, Nadira is saying, this, maybe it feels familiar to teachers that this is how those teachers learned it. Maybe they don't really understand linearity themselves that deeply. Maybe that's just how the textbook says to do it. And so I would tend to agree. Another one might be that they feel constrained. So it may not be, a teacher's quote unquote fault, whatever that means. I mean, perhaps it's because they're saying, we've got this test at the end of the year. The standardized test is going to look a lot like this. And so I need to teach towards that. And so I just feel constrained. I don't feel like I have flexibility to teach it in any other way. And I think that's certainly understandable. All right. So ineffective though it may be, I think we can agree that there are reasons for it. Okay, so now let's come back to this. Oops, let me pop through this, pardon me. All right, so what I'd like to do now is just show you guys the work that we're doing at Mathilicious and how do we address linear functions. And in particular, how does that lead into project-based learning? So we'll get into this in a moment, just to give you guys some background. At Mathilicious, we spent working with Buck Institute. From October to December of last year, we were piloting some project-based learning resources in a very large public district outside of Richmond, Virginia. And so we did over 3 cohorts over 3 months. We were in, I think, 25 classrooms, exploring what does effective PBL look like in a traditional math class. So in a school or in a district where they haven't done much project-based learning, what works and what doesn't work, and how do we craft resources that can help teachers incorporate more PBL and PBL type activities into their instruction. And over the course of that, here's what we learned. And I'll explain how this informed the decisions that we made. So one thing we learned from teachers is that they want to, oh good grief, come on computer. They want to incorporate more project-based learning into their instruction. So many teachers look at PBL and they say, this is the kind of stuff that I would like to be able to do. However, I'm not ready for full-on PBL. Right, so maybe I have been teaching for a while in a very traditional way, and PBL feels a bit outside of my comfort zone, maybe even way outside of my comfort zone. And so I need some more support in how to do that. So what teachers often ask for is, instead of going towards full-on PBL, very authentic student-led project-based learning, they were asking for more of a balance between something that's relatively scaffolded and something that is still inquiry-based, that really has those key elements of PBL that are student-directed. And so trying to find a balance between those. And the fourth one that they said is, and I imagine a lot of teachers will understand, math teachers said, we want this to be teachable within a week. Maybe we'll allocate 2 weeks, but if you're asking us to do a project that's going to take more than 2 weeks, we may have a really difficult time justifying integrating that into our scope and sequence or pacing guide or whatever, because we just, again, feel so constrained. So let me X out of here and just see what people think about the teacher feedback. Is it surprising, or can you understand where these teachers were coming from? Okay, Laura says she thinks it's reasonable. And again, just to put this in context, this was, this is a public school district in Virginia. It's not like high-tech high, so these people aren't, these teachers and classes aren't super accustomed to this. Yeah, so it doesn't surprise me as a math coach. All right, so Nadira sees this all the time. Okay, so now I will just show you kind of what our takeaways were, and then we'll get into a sample project so you guys have an idea of the kinds of resources that we're creating. So let me just pop through this teacher feedback. Okay, so what we did is we walked away and we said, okay, so teachers are asking for something that will take place over the course of a week, but not extend into the next week. So we are sort of interpreting a week as a hard stop. And I should say that the school district where we were is teaching on 80-minute periods. So if you're on 45-minute periods, this could very well double into 2 weeks. And if you can justify doing it, great. And if not, there was nothing that we could do to kind of strip it away in half. So we said, okay, we figured that the first 2 days needed to be a core lesson that was a bit more scaffolded. This is getting back to that balance that teachers were asking for. So Monday and Tuesday was a core lesson to contextualize the skill. Wednesday and Thursday then became these project extensions. This is where the kind of PBL element fit in. And Friday was presentation day. And when we did something like this in our Chesterfield pilot, or rather our Virginia pilot, it actually ended up working really well. And so these are the types of projects that we're creating now. And so let's look then at an example. We have a lesson called the Domino Effect. I will tell you now that the project extensions and the project materials are not available on the site now. They'll be available in the fall, but this will give you guys a bit of a sneak peek in what we've been working on. So we have this project or lesson right now called the Domino Effect, and it explores Domino's pizza pricing. So right now we're going to look at the core lesson, that Monday and Tuesday lesson. And so the question is, at Domino's Pizza, this is in Washington, D.C., a 2-topping medium pizza costs $14, and a 4-topping medium pizza costs $17. And the question is, how is Domino's charging for pizza? So how much are they charging per topping? And what are they charging for the base price of the pizza? So here's our situation. And I'll just pop through this pretty quickly because I imagine everyone here can figure it out pretty quickly. But we know that when we buy 2 more toppings, then the price goes up by $3. So in the chat window, how much are we spending per topping? I can't see it, but I would imagine that most people are saying $1.50 a topping. Perfect. Now the next question in this scaffolded narrative is, for a 2-topping pizza, or rather for each pizza, how much are you spending on the toppings themselves? Well, at $1.50 a topping, a 2-topping pizza, we're spending $3 on toppings. And for the 4-topping pizza, we're spending $6 on toppings, right? So that's our MX part. But of course, the prices of the pizzas are actually higher. In both cases, $11 higher. So what does that $11 represent? That represents the base price. And so now we know everything that there is to know about how much Domino's is charging for a medium pizza. They're charging $11 plus $1.50 per topping. Now, if you'll notice, this is exactly the same problem as the rote traditional method from before. The difference, of course, is it's been contextualized to help a teacher teach it to her students or teach it to his students in a way that's a bit more meaningful. Okay, so what happens next? Well, now we've got to look at the small and the large pizza. We did the medium, now let's look at the small and the large. And so with this screen up, take 2 minutes and try to figure out how much Domino's is charging for the small pizza and how much they're charging for a large pizza. And I will X out of this. Hopefully you guys can still see it. Okay, so again, the question is, how much is Domino's charging for the small and the large pizza? Can you come up with that linear function? So let's start with the small. In the chat window, can you type in how much you think Domino's is charging per topping for the small and how much the base price is for the small? Or if you prefer, write the linear equation for the small. Let's type that in and see if we all get the same thing. Now, of course, it would be really great if someone would invent a technology that would allow everybody to type it in and then see what their peers got. But we're pretty low tech right now. But somebody should invent that. Okay, so it looks like everybody is pretty much getting the same thing. Then it looks like Domino's is charging $9 for the base price and $1 per topping. Perfect. What about for the large? If you didn't type it in before, if you didn't do the small, type it in for the large. Let's get everybody involved in this. Okay, so we've got Sherry says $13 base price, which we see here. And so really it's just a question of the toppings. Now, Sherry, let me ask you, when you got $1.70 per topping, was your thought process, did your thought process sound something like, when I buy 4 more toppings, then the price goes up by $6.80? Is that sort of how it sounded in your head? Is that how it sounded in everyone's head? No? Sherry, how did it sound for you? What was your kind of internal monologue? Well, while Sherry is typing, it sounds like a lot of people said, yeah, I did think of it in terms of when I buy 4 more toppings, then the price goes up. Oh, okay, so you said I just subtracted 13. Okay, so it sounds like, Sherry, you sort of knew the process in your head. But it sounds like a lot of people are saying, when I buy 4 more toppings, then the price goes up. Now, isn't that interesting? Because what we're saying is when X changes, then Y responds. If you think about it, that's exactly the opposite of rise over run. Right? When we teach rise over run, essentially what we'd be saying is the price goes up. First, the price changes, and then we get more toppings. So we're like, yo, Domino's, here's $6.80 more. And Domino's like, well, I guess I better give you 4 more toppings, right? Which, of course, is not how it works. So when we think of the traditional way of teaching rise over run or slope, we can actually create a misconception just in the way we articulate slope. Okay, so it sounds like everyone's pretty much on the same page in terms of how much Domino's is charging, and this is what the prices we would expect them to be. And it looks like everyone pretty much got these linear equations for small, medium, and large. All right, so at this point, we have pretty much done, that is the core part of this lesson, right? So that's the Monday and Tuesday. And just to show you the standards that have been addressed, and I want to make clear that these are the standards that were addressed but not covered. Students still need to develop that muscle memory, go do some practice, understand slope as slope and not just cost per topping. But the standards that were addressed in this were graph proportional relationships, interpreting unit rate as the slope, so cost per topping, coming up with a linear function, y equals mx plus b. We did solve real-world mathematical problems leading to linear equations. And then we have all of these function standards. Just to put this in perspective, that's actually 28% of the Common Core standards for 8th grade. So a teacher who teaches this is able to get through a lot of material when we contextualize math. We're able to get through a lot of material in a way that makes sense to students. And so then when we transition from this to abstracting the math, understanding slope as a rate of change, then students will have a more of a kind of a foundation to be standing on. And if they slip, then they slip less far, right? Because the teacher can say, well, just think about it like Domino's Pizza. Okay, so that was the core lesson that we've done. And to help students teach this, just so you know kind of how Mathalicious works, we provide teachers with a multimedia presentation that will have any graphs or charts or videos, a student handout that kind of scaffolds that narrative. So if you look at this handout here, you can see the questions that we just did, and a lesson guide to help ensure that teachers are able to teach this lesson well. So misconceptions that may come up, we'll try to address those in the lesson guide. So that again was the core lesson. Here is a piece of student work. A teacher in North Carolina taught this a couple weeks ago. She taught it to her 7th graders. And here is a picture of their handouts. And as you can see, and as she said, every 7th grader got the correct equation. They all got the right thing. And she says, this is great. This makes me feel good. It feels like I've taught them stuff, right? So core lesson sets this teacher up to contextualize linear functions, right? And this is exactly when we were talking with the school district for Virginia, this is exactly what the teachers were saying. We need something that's relatively scaffolded, right? Because we're math teachers and we oftentimes don't feel like we have the flexibility that a social studies teacher, an ELA teacher might have. So we've done that. So that again is the core lesson. So now let's take a couple minutes and look at the project extensions, where this starts to become more PBL-y. So here's where we left our conversation. We have the small, medium, and large pizzas. And we've got the base prices and the cost per topping. This is what we expect. However, it turns out that if you look more closely at Domino's Pizza pricing, their pricing actually looks like this. At least in Washington, D.C., if you are paying for a small, for instance, $9 for the base price and $1 per topping, but at 4 toppings, they stop charging you. And they don't charge you for any more toppings until 10. Now let me X out of this for a moment. And I'd like people just to take a couple minutes and chat back and forth. And the conversation here is, are there any questions? Are there any questions that you think naturally arise from what we just found out about Domino's Pizza pricing? So do you have any questions based on what you're seeing on this screen? Or put another way, could you imagine any projects extending from this? HDCH is saying it still doesn't tell the kids what is the better buy. Can you flush that out a bit more? If you were a student, how would you go about figuring out which one is the best? So again, the question on the table is, now that we know, now that we've contextualized linear functions, and now that we're looking at how Domino's is charging, are there any questions that you have? Cost versus area. Okay, so HDCH is saying cost versus area, which I assume you're getting to kind of cost per square inch, which is the best deal. Laura's saying, are they overcharging for the first 4 toppings, right? Like maybe, so if I'm understanding your question right, Laura, maybe Domino's is ripping you off for the first 4 and then they're like, whatever, after 4, like we're gonna stop bilking you. Okay, maybe. Interesting to see difference in topping prices for the different sizes. Tracy, that's an interesting point. Can you flush that out a little bit more? Could look at the weight of each size of topping. Okay. Figure out the price of cheese, sauce, and okay, so it seems like, here's what's really, it seems like there are a lot of questions. You know, Tracy's like, look, maybe we need to actually weigh each topping, right? So if you could order 3 pizzas, maybe you would weigh the pepperonis and see, I assume, see if you're actually getting enough for your money, right? Tracy's like, yo, why does it go from $1 to $1.50 when you go from small to medium for the per topping price, but it only goes 20 cents from the medium to the large? Why is that, right? Somebody earlier, let's see, somebody earlier said, oh, good grief. Oh, HDCH said, what? Somebody else said, like, what's the best deal, or what about other pizza places? Paul says, are you getting the same amount of toppings but simply more variety? We don't know, right? So all of these questions, we have Domino's in Mexico. Okay, so Inns is saying, look, what if we compared it nationally? Maybe Domino's in Mexico is different than Domino's in the States. Okay, so there are a bunch of questions that could come up. And I'll just walk you guys through briefly some of the project extensions that we proposed to teachers and students. And of course, if they come up with their own, they're more than welcome to pursue those. But one of the questions and one of the problems that we asked is similar to one that came up earlier, which is when you go from a small to a medium, your per topping cost goes up by 50%. But are you actually getting 50% more topping? Right, that was one question. Another question that we asked was, why does Domino's stop charging after 4 toppings, right? Are people actually ordering more than 4 toppings, or is it just kind of a marketing ploy? Like, you know, whatever. That was another question we had. And another question we had was similar to Inz's question, which is, what about, you know, Domino's in other places, or what about other pizza restaurants? And so just so you guys get a sense of the types of projects we're creating, what we'll do at Mathilicious is we take this after the core lesson and we provide teachers and their students with materials that are somewhat scaffolded, but much less so. So we'll offer suggestions on, here are some ways to think about this. For instance, chain gang. How do other national pizza chains charge for their pizzas? Or another project, top it like it's hot. Why does Domino's stop charging after 4 toppings? Right? How many people actually order more than 4 toppings? Oh, and another thing, they cut you off at 10. I should say that if we go back and look at the graph, Domino's will not let you order more than 10 toppings. On the website, it says your pizza won't cook well, but who knows? Maybe they're just trying to protect themselves from the person who wants to order 1,000 orders of pepperoni. All right, so we've got chain gang, we have top it like it's hot, and then the third one was cover me. When you increase the size of a pizza, do you get enough additional pizza base price or enough topping to justify that price increase? So again, these are the project extensions, and we'll just look for a moment at some of the presentations. So that teacher in North Carolina who taught this over, I think, two weeks ago, here are some screenshots, or here are some pictures from her class. So this is a student who was looking at Domino's Pizza versus Ella's, which is a local chain. And so you can see the linear functions that she's doing. Again, 7th graders. Here is the one about, why does Domino's cut you off at 4? I'm sorry, why does Domino's stop charging for additional toppings after 4? And so these students went and did a survey in their class, or rather in their school, to see how many people order how many toppings, right? And so you can see that here, about on the left in that first bar, about, I don't know, 13, 14 people that responded to their survey don't order toppings at all, so they're just cheese pizza. But you can see that not many people are ordering more than 5 toppings. Students on the right chose to present their data using a pie chart, which I guess is entirely fitting given the topic. Given the topic. All right, so that was that one. And then this is a really interesting one. So this is the top it like it's, or cover me project extension about, are you actually getting your money's worth? And let me X out of here and I'll zoom in because we're all math teachers. And so I imagine we'd all like to see the numbers that are going on in here. But on the left, what the students did was they calculated the difference in area, right, as a %. So if you look at going from small, and here's my mouse down here. Hopefully you can see my mouse. When they went from a small to a medium, these 7th graders said that's a 56% increase. But there is a 49% increase in the topping price. It's actually $1.49. Just for the sake of this, I made it $1.50 to make it easier. And so they're saying, you know, you're only paying 49% more per topping, but you're getting 56% more pizza. And so they would say that's a great deal. And they did the same thing for a medium to a large. Another group showed this differently, right? They chose to show it, it's the same information, but the way that they represented it was actually a bit different, right? So you can see here, they've got the orange, which was the pizza price. It went up 22%, but the topping went up 50, or topping amount rather, area went up 56%, which is exactly what they got over here. And so that's really nice. You can see the amount of math that's going on in here. So we've got linear functions, which lends itself to, in the case of these folks, they're doing some survey data, right? So they've got bar graphs and the kind of statistics stuff in there. Here they're doing area of a circle. Other groups, and if you think about it, this is actually really savvy, other groups, when they calculated the areas, they took out the crust. They didn't calculate the crust, and they calculated the percent change of the inside to another inside. Why do you think they did that? Yeah, you don't put topping on the crust, right? So these students are like, yo, why should we take into account the crust if we're not putting topping on there, right? And that's fantastic. Incidentally, who knows? Maybe that's why Pizza Hut offers stuffed crust, because it was wasted real estate. Anyway, so as you can see, there are actual students doing these projects, and it's really nice because for this teacher, this school is one that is more accustomed to project-based learning. But for the traditional, quote unquote, traditional teacher, someone who's more accustomed to the type of rote instruction, you can see how this type of activity would help ease them along, would help move them along on that spectrum from kind of rote procedure to more inquiry-based. So these project extensions were somewhat scaffolded, but they're much more along the lines of, like, here's some suggestions, and however you choose to approach this, it is sort of on you. All right. So any questions at this point? We'll have time for questions in about 5 minutes. But any questions on this? Cool. Right on. Well, then let's just finish this up, and we'll get to the end, and we can all kind of wrap in the chat if this lets me. No, of course it's not going to do that because Murphy has totally taken control of PowerPoint. So anyway, so that is Domino Effect. And after that pilot in Virginia, we at Mathilicious walked away and we said, wow, these project extensions are really powerful. These really do put teachers in a position and their students in a position to engage in the mathematics in a way that's incredibly authentic and allows students to really take ownership over their work. And so what we've done is we've said, okay, well, we want to create project extensions for all of our lessons. And I'll just give you 3 examples of how we're doing that. So unfortunately, I can't animate, so I'm just going to delete some of this out. Thank you, Microsoft. You guys are awesome. So one is tip jar. So the question here is, how should we tip in a restaurant? So these are from, oh, good grief, I was pressing the wrong button. Son of a gun. My bad. All right, so one lesson is tip jar. How should we tip in a restaurant? Because if you think about it, when you tip in a restaurant, you're paying someone based on how expensive the menu is, right? So if somebody brings me a $30 steak and I tip 20%, I'm going to give them $6. But if they bring me a $3 plate of pancakes, cupcakes, I'm only going to give them 60 cents. So I'm paying them based on how expensive the thing is on top of the plate. This is a 6th grade lesson on percents, but you can imagine, for projects here, students will research different types of tipping in different industries in different countries and come up with what they think is the fairest way to tip. That's tip jar. There's another one called on your mark. If you watch the Olympics this summer, you know that Usain Bolt dominated like he did the previous Olympics in 2008, and he is incredibly fast, but he's also very tall. And so here, the question is, do taller sprinters have an unfair advantage? In the core lesson, that Monday and Tuesday part, students explore what would have happened if Usain Bolt had to run farther than everybody else. So if Olympic distances were based proportionally on height, it turns out that he would have not won. In fact, he wouldn't have even gotten a medal. So that's what happens in the core lesson. And then the project extension, students go out and run themselves and see whether taller students tend to win. They analyze historical Olympic data to see whether taller athletes do have an advantage, and if so, in what events. And they take an event and recalculate it retroactively, or rather they recompete it retroactively to see what would have happened had it been organized proportionally. So maybe Michael Phelps has to swim a couple more laps. And then for high school students, so tip jar is 6th grade, on your mark is 7th grade. And for high school students, here's one called Xbox Exponential. The question is, how have video game console processor speeds changed over time? There's something called Moore's Law that predicted, a computer scientist in the 60s, one of the Intel co-founders, predicted that computer processing speeds would double every 2 years. In the core lesson here, students determine the equation, the exponential growth equation based on Moore's Law, and use that to see whether video game consoles, Nintendo Entertainment System, Xbox 360, the new Wii, have kept up with that pace. And then they can extend that into some pretty radical ways, into some pretty radical areas. For instance, how have other technologies evolved over time, but also, could you imagine a moment where video games would be so realistic that you could actually live inside of them? And based on what we just found out about exponential growth, when would you expect that to happen? So that's a pretty heady one that's happening at the high school level. So, oh, good grief. So that is what we're doing at Mathalicious, taking these lessons and developing projects on top of them, and trying to put teachers in a position to teach the standards that they need to, and in a way that really pushes their students to think about the world a little bit more critically. So, with that said, let's just have a little wrap session. Does anybody have any questions about anything I said, or pushback, or feedback? Okay, that's a great question. So with this model, how can we ensure that the core y equals mx plus b is still understood by all after the extension? And I assume, and correct me if I'm wrong, I assume that what you mean by that is, are students actually learning deeply linear functions? Is that sort of what I'm hearing in your question? Is what I'm hearing in that why a yes? That's a great question. And this is why I think it's so important to clarify between covering a standard and addressing a standard. So I think probably in a presentation at NCTM once, I think I might have showed something similar to this and said, this lesson covers this. And I got a lot of pushback from people who were right to push back. So that's a great point. So I'm going to address what you just commented on in a moment. But when we contextualize these skills, using Domino's pizza pricing to contextualize linear functions, this is by no means all you're learning for linear functions, right? The goal with that lesson is merely to contextualize a situation that is linear, so that students have some vocabulary around slope. For instance, they're thinking of slope as cost per topping, or they're thinking of the base price as the value when there is no x, right? Or when x is 0, rather, in this case, the base price. But there's still a lot of work to be done to abstract from that, kind of from that concrete situation to a deeper understanding of slope as a rate of change. We at Mathalicious, we don't write lessons that do that. There are plenty of people that do. And some of the stuff is really good. Our goal is merely to put you in a position, or rather the teacher in a position, to, when you are abstracting it, you can go back to something concrete. So kind of giving students a foundation to stand on when they then do abstract it. And after all, I mean, abstract is sort of is naturally what comes after concrete. And then, of course, what we do, our real bread and butter is, once you are really good at linear functions, we can give you a whole bunch of other ways to apply that in other situations. So HDCH followed up and she said, as some students do the pie graphs, there didn't seem to be a linear model. That's absolutely true. So the core lesson is what is aligned to the standard, right? So the core lesson is what addresses those linear functions, equations and expressions, functions, standards. That's where a teacher says, okay, I need to address linear functions. I'm doing that here. But then, of course, the lesson lends itself to whatever question it lends itself. This student here did use linear functions when exploring other pizza chains. These students, of course, didn't. This is more survey data, right? And some pie chart stuff. And I think, to your point here, this is area of a circle, which is actually a 7th grade standard, not an 8th grade standard. However, it's still a really good project, and one that is worth exploring. And so part of the rationale for that core part, Monday and Tuesday, and then project extension for the rest of the week, is the teacher can say, look, I've addressed my needs, my linear functions needs, and so now I can justify to myself doing some stuff that, you know, may not be related to linear functions, but certainly related to Domino's pizza pricing. All right. Were the students teamed in the extension portion? They were. And that's a great question. We try to write projects and materials that really foster and really encourage small group instruction, or rather small group work, and then large group presentations. And that's exactly what happened here. I would imagine that this would be a bit of a drag if people were working on this alone. And it is worth, I mean, just as an aside, with all of the attention on online learning and individualized instruction, you know, at the end of the day, school is plural by definition. Like the fish taught us that. And there's something really nice about school being an opportunity for students to socialize with one another and interact with one another and learn those types of, you know, community team building, you know, just collaboration skills that oftentimes we really lose in middle school. And so everything that we create really revolves around that human group experience, and creating a really healthy, I think, interchange between a teacher and their students. So hopefully that, Talani, answers your question. Does Mathalicious provide rubrics for assessing the extension projects? We sort of do, and we sort of don't. So honestly, grading this stuff is really difficult. And coming up with an effective rubric is difficult. What we do provide as part of these, and what we're working on now, is we provide a teacher guide that says, like, here's what your students might come up with. So the area of a circle thing, you know, in the teacher guide, it says, here's one way to think about this. What we hope to provide, especially as more teachers give us feedback like this, is we would love to be able to offer examples of student work, right? And then, can users suggest ideas for projects on the website if we don't see one? Absolutely. I mean, you can feel free, please email us if you have extension activities, you know, for these lessons that you think would be really great. But even if, of course, even if we don't use it, or even if we don't kind of codify it in our resources, I think what's so nice about these real world contexts is all Mathalicious is doing at that point is saying, like, hey, here are some doors you could open, but if you've identified other doors, have at it. Like, that's what teaching is about. So we try to be as invisible as possible, just because, you know, all we do is write the lesson. You know, it was Julie in North Carolina. She taught it. Like, she's the superstar. We're just kind of behind the scenes writing stuff. Does Mathalicious cost? It does cost. We have bills to pay, as I'm sure you can understand. So we have a price for schools and districts. And that's, right now, it's $185 for an annual account for teachers. However, if you're a teacher paying out of pocket, we actually allow teachers paying out of pocket to to pay what they can. They can choose their own price, and there are a couple options for them to choose. And there's no difference. It's just really a function of, everyone at Mathalicious has been a teacher, and we don't want something as kind of arbitrary as money to get in the way of a teacher. If a teacher looks at Mathalicious and says, look, this can really help me engage my students, and I'd love to be able to incorporate this into my classroom, we don't want money to get in the way of that. At the same time, we don't want teachers to have to pay for it anyway. That's why schools have money for curriculum. But when that becomes cumbersome, we try to do everything we can do to make it accessible, but also pay for our electricity. Do we have lessons available in Spanish? We don't. We will. We definitely have plans to translate all of this stuff into Spanish. Pero ahora todo es en inglés. Bueno, nada. ¿Y dónde estás en México? I don't know where that is. Bueno, yo pasé un verano en DF. Anyway, so are there any more questions? Anything we want to rap about? Well, maybe we could do Twitter Math Camp next year in Mexico. Dan, what do you think about that? You're at the Thomas Jefferson Institute. Well, I'm in Charlottesville, so there should be a Pacific Coast side. Nice. I think that I have a feeling this is going to be a really great point. So I think that many teachers avoid PBL because they don't know how to grade it. I think maybe that's true. Let's see. Without having an idea of the possible outcomes of the extension project, it's difficult for teachers. Yeah, exactly. I think the providing student work is sort of the best thing. Of course, when you're rolling out content, you're rolling out before there are examples of student work. But I think down the road, especially as more and more teachers start to use these, I think, Kate, you're absolutely right that's great. In the meantime, what we can do is exactly what you said, is say, look, here is where a teacher could take this, because we really want to make that transition to PBL as graceful as possible. Talani, I'm not really sure what you mean by rigid motions. And I'm getting pinged from Al, our buddy at BIE, that it's time to wrap this up. But if you have any questions, and transformations. Yeah, we actually have an awesome one that we're writing about Mario Brothers. It's going to be bananas. So anyway, I think we've got to wrap this up. But if anybody has any questions, feel free to email me. My email is karim@mathalicious.com, or you can follow us on Twitter at Mathalicious.